Hey y'all, it's your personal math teacher, Mr. Boyden. I'm back at it again, and today we're going to be looking at confidence intervals and significance tests for differences in means and proportions. The thing that's going to be different today, and it's hinted at here when we say differences, and that means like difference like subtraction, is that we're essentially looking at two samples or two groups today. What we've done prior to this is if we had a single sample or a single group looking at confidence intervals or t-tests or z-tests for those. Today it's just two samples or groups. Okay, so the three things we're going to look at today. We're going to look at the sampling distributions when you have two samples or two groups. We're going to look at how the conditions for inference are different and not different when you have two samples or two groups. And then we're going to do some examples and see how similar these are to what we already know. So let's get right into it. Let's take a look at the sampling distributions when you have more than one sample. Here it is for a proportion, and I want you to notice this top row. This is stuff that should be reviewed. That's already familiar to us. So what's going on in the second row? Well, this is just the Pythagorean theorem of statistics right here. Okay, that's what we saw actually quite a while ago. That's how this is getting put together. So it's squaring this value and the square root goes away. And notice there's no square root on that individual term. And same thing again over here, square them, add them, root them. That's what the Pythagorean theorem does. Okay, now how is it different for means? Take a look at what it is for means. Again, the first row is total review, okay? And the reason I'm showing you this now, mostly, we're not gonna do these by hand very often, but this is to give you an idea of what's going on in the background in your calculator when it's generating either a confidence interval or finding a p-value for you. Occasionally on a multiple choice test, we will be asked to basically select which of the following equations or expressions would represent the p-value or something like that. And so we do need to be able to refer to these setups and know what gets plugged in where. Okay, and by the way, the ones and the twos in here, that's just referring to sample one or group one and sample two or group two. By the way, exact same thing here. Pythagorean theorem of statistics is how they're putting that together. It's just this thing right here, the original standard deviation, getting squared, added to itself, and then having a square root taken of that. Okay. What about the conditions? We're going to look at this in the same way. We're first going to look at what we already know the conditions to be for one sample. So let me make a note right here. This one sample stuff, that's total review. Let's take a look at two samples with proportions. First of all, we still need to have random samples. It's just that we need to have random assignment in the experiment, or that we need to have randomization for both groups. The 10% condition still applies. It needs to apply to both samples. That's all this says right here. So you're going to have to do it twice. You're going to have to check that condition twice. And then it's still the large counts condition, but it does have to apply to both samples. So count them. It's not 1, it's not 2, it's not 3, but it's 4 inequalities. And all that's saying is that it does need to apply to both samples. Now what about for means? How is that similar? How is that different? Okay, random sample or experiment. Okay, not surprising. We still need the 10% condition, and we still need to have normality of the sampling distribution, and that's going to be the same methods as if it was one sample, but it's just that both samples have to meet that criteria, or meet the criteria for being normal or approximately normal. Okay, there is a little bit of a caveat here though. Let's take a look at that. Okay, there are some times when we don't do the 10% condition. We don't do that on chi-squared tests. We haven't learned that yet. That'll be in an upcoming video. It's typically not used for differences of means, which is one of the things we're doing today, but check this out, except when there's really small populations or really large populations. And we don't use them for randomized experiments. It's not necessary because you're not concerned about independence of the sample in a randomized experiment. So this one, the second one, can be a little bit puzzling, like, wait, what's extremely small or extremely large? Well, we'll talk about that as we go a little bit, but when in doubt, check the condition, okay? In most cases, the 10% condition is going to apply almost, yeah, it's pretty much always going to apply. So when there's doubt, just check it. All right, let's do some examples. Here's going to be our first one. Mr. Wilcox's class performed an experiment to investigate whether drinking a caffeinated beverage would increase pulse rates. 20 students in the class volunteered to take part in the experiment. All of the students measured their initial pulse rates in beats per minute. Then Mr. Wilcox randomly assigned the students into two groups of 10. Each student in the first group drank 12 ounces of cola with caffeine. Each student in the second group drank 12 ounces of caffeine-free cola. All students measured their pulse rates again. The table displays the change in pulse rate for the students in both groups. So let's check out our data. So for example, this student who had an 8 in the very beginning over here, that means that after drinking the caffeinated cola, their pulse rate went up by 8 beats per minute, I guess is what that's saying. All right, what's our prompt? We are asked to construct and interpret a 95% confidence interval for the difference in true mean change in pulse rate for subjects like those who drink caffeine versus who drink no caffeine. All right. Anytime we do inference, we want to do this as a state, plan, do, interpret. So let's get started with a state. Our statement is going to be that we're looking for the difference. Now, what did they say? The mean change in pulse rates for subjects like those who drink caffeine. So I'm going to go mean for caffeine minus mean for, I'm going to call it NC, no caffeine. Okay, and so what's going to be the mean difference? And it's just going to be rewriting this statement. Then we look at the plan. And let's go look at the calculator really quickly because we need to name the type of interval we're constructing. So let me pull up my calculator. Let's go look in the menu. We're in a stats class, so go to statistics. Let's go to confidence intervals. And so what do we have in here? We have, let's see, this is a question about means, so it's a t thing. In the past, we did t interval, but there's 2 samples. We'll look at that. 2 sample t interval. So that's what we're going to end up using. Let's go back. We need to let our graders know what we're doing. We're doing a 2 sample t interval for difference in means. Okay, and then we need to start checking some conditions. So conditions, number 1 is randomness. And did they say in here it was randomly assigned, says it right there. So we'll just make a note that the question said randomly assigned. Randomly assigned. Do we need to check the 10% condition? No, we don't, because we saw a minute ago that if you have a randomly assigned experiment, which is what this is, or a difference in means, that's also this, then you don't need to check the 10% condition. We do need to check for normality of the sampling distribution, or approximate normality, I should say. And so how can we do that? So this is mean, so it could be the central limit theorem. Each group only has 10 subjects, so it's not that. What else could it be? It could be that they told us, no, they didn't tell us. So what we're going to have to do then is we're going to have to make a dot plot of the data in our calculator, and we're going to have to assess our samples for skewness or outliers. So let's go do that now. So open up your calculator, and I didn't click that test yet because we're not ready to do the test yet. So I'm going to come in, let's add a page of lists and spreadsheets because I'm going to need to type in those data here. And I'm going to call that calf versus no calf, and then we'll type that in real quick. With our data input done, let's go visualize the data. So add a new page. Let's make that a data and statistics page. And I'm going to set it up right now so that we can see both at the same time. So let's split the page. And we'll do one for the caffeine and one for no caffeine. Do we see any obvious skew or outliers? Might be a little tempting when you see these extra dots over here. One way you could think about it is if one of those dots was not there, would you still think that it was skewed? One dot doesn't make skewness, so no, there's not obvious skewness or outliers. I might wonder if that's an outlier. Remember, a quick way to do that is if you turn this into a box plot, that'll tell you if it's an outlier. Nope, there's no dot down here. And so, do we meet that condition? Yeah, and it feels kind of cheap, but essentially, yeah, we do. Okay, so no outliers or skew or no clear skewness in dot plots. So we meet that condition, which means that we are ready to construct our confidence interval. So state, plan, let's do it. And we're going to do it in the calculator, not by hand. And we'll go back to our calculator screen over here. And let's go construct our interval. Statistics, confidence intervals, 2-sample t-interval. I want to strongly suggest that you choose data as your input option because we just spent all that time typing in the data. Let's use that to our advantage. And then I just need to let the calculator know what I'm going for here. I want caffeine and no caffeine. Don't worry about frequency. We didn't have any frequency lists. And so, yes, confidence interval of 95%. Let's see what we get. Looks like 2.5. Oh, nope, I'm scrolled down too far. Hold on. I wonder if your calculator has that same issue. So there we go. Negative 1.3 to 3.7. Okay, and I've recorded that in my notebook. And so now we're asked to construct and interpret. We've done the construct part. Now it's time to interpret. How does the interpret statement go? Okay, it always goes the exact same way. We are 95% confident that the interval from those two numbers, so from negative 1.30 to 3.70, captures the difference in pulse rate change for subjects like those in the study who drink caffeine versus those who do not. Okay, and that's just copy and pasting from the state up above. So people, that's it. Okay, a few little differences between this and what we learned previously with confidence intervals, but by and large, similar stuff. Let's get some more examples. Okay, here's the next one. A Pew Research Center poll asked independent random samples of working men and working women how much they value job security. Of the 806 women, 709 said job security was very or extremely important, compared with 802 of the 944 men surveyed. Construct and interpret a 95% confidence interval for the difference in proportion of all working women and men who consider job security very or extremely important. So what are we going to state? We're going to state they said the difference in proportion of working women and men. So I'm going to go P sub W for the proportion of women minus P sub M for the proportion of men. And that's referring to basically what the question asked, the difference in proportion of all working women and men who consider job security very or extremely important. Now all I did there is pause my recording and type in what the question asked. And so they kind of have told us what to do there. Let's go with our plan. Okay, we're going to take a double check in the calculator to make sure we know the name of this confidence interval. So menu, statistics, and let's go look at our confidence intervals. Now remember, if it has one sample, we'd call it a one prop z interval, as in a one proportion z interval. Well, we have two different proportions, one for men, one for women. And so we're doing a two proportion z interval. So that we'll be coming back to that in just a minute. Okay, let's go set that up over here. Our plan is a two proportion z interval for a difference in proportions. And we need to name out our conditions. Number one, we need randomness. And so did they tell us that? They said independent random samples. And that covers both samples in one move. Do we need to do the 10% condition? It's a proportion, so yes, the 10% condition. So what are we looking at? We surveyed 806 women, and they were samples of working women. So we're going to say 806 is less than 10% of all working women, which is pretty obviously true. And there were 944 men. So we're going to say 944 is less than 10% of all working men, which also seems to be obviously true. All right, so that one's satisfied. Now we need to satisfy the large counts condition. And so this is going to potentially have just a little bit of extra work to it. So I'm going to break this up. Let's do it for women first. Women, we had 709 out of 806. 709 out of 806, that's the proportion. And remember, it's n times p, so sample size is 806. Now, look at what happens when we set this up. So I'm going to put the format n1 times p1 needs to be greater than or equal to 10. But look, those 806's cancel, so this says 709 is greater than or equal to 10, so we're golden. Now we need to do the complementary proportion down here. And so if we had 709 women who said it was super important, I believe that leaves 97 who did not say that. So 97 out of 806, sample size of 806, and the same exact mathematics is going to happen here. The 806s are going to cancel, and 97 is greater than 10. So what we just showed right here is that the large counts condition does apply to the women in the sample. Now we need to come over and check the same thing for the men. And so we had 944 men surveyed. And how many of them said it was important? 802 out of the 944. And what about the complementary probability or complementary proportion? So if 802 said that it was important, that means that 142 said it was no biggie, I guess, apparently. I don't know why they would say that, but I guess it's not important to them. Okay, 944, and we cancel these out. Both of those, so we have 802 and 142, both of those are clearly greater than or equal to 10. And so we satisfy the large counts condition. Now that might seem like a lot of work, guys. You have to. If it's 2 samples, you're going to have to write out 4 different inequalities for the large counts condition. We unfortunately don't have a good way around that. All right, we've done the state, we've done the plan. Now it's time to actually go construct and do the do part of this. So back to the calculator we go. We said we were going to do a 2 proportion z interval, so there it is. Let's pull that up and let's see what information is needed. All right, they want successes and basically the sample size. So we said we were going to do women first, so let's do 806 is the sample size of women. And there were, of those, 709 women said that it was super important to have job security. Now we'll put in the numbers for the men. Only 802 men out of 944 felt that that was important. I'm going to go real quickly and check what confidence level they wanted us to have on this one. They did say a 95% confidence level, so we need to put that in. It's already there. Awesome. Let's see what we get. All right, and here's my result. It basically just spoon feeds me back all the information that I was looking at and that I was typing in. The one thing that's different is now they're going to tell me the lower and upper limits of my confidence interval. So let's make a note of those. I'm going to go jot those back in my notebook over here. And so my interval ranges from negative 0.0019, I'm going to call it 002, just so I don't have too many decimals, and then 0.062. So around 0% up to 6%, it looks like, basically. Okay, that's the state, that's the plan, that's the do. Now we need to interpret. So maybe if you haven't, you want to pause the video and finish writing out this statement yourself. We are 95% confident that the interval from negative 0.002 to 0.062 contains the difference in proportion of all working women and men who consider job security very or extremely important. Guys, check that against what you wrote. The thing that I sometimes see students leave out is this part of all working. Okay, so sometimes you say like, oh, the difference between men and women, but it's not just some men and women, it's all working men and women. So be careful about that. That is something that graders can be pretty particular about. So look out for that. All right. Okay, here's another one. To study the long-term effects of preschool programs for poor children, researchers designed an experiment. They recruited 123 children who had never attended preschool from low-income families in Michigan. Researchers randomly assigned 62 of the children to attend preschool, which was paid for by the study budget, and the other 61 served as a control group who would not go to preschool. One response variable of interest was the need for social services as adults. Over a 10-year period, 38 children in the preschool group and 49 in the control group have needed social services. And we're asked, do the data provide convincing evidence that preschool reduces the later need for social services for children like the ones in the study? We need to justify our answer. All right, so read that clearly. They asked, do these data provide convincing evidence? That verbiage right there is an indication that we're going to need to do a test. Okay, and so it is going to be state, plan, do, and interpret. So let's start listing out what we're going to do here. So we're going to state, and what do we need to include in the state? We need hypotheses, we need parameters, we need statistics. So let's name out our parameters first of all. So it is a proportion question, and we had children who went to the preschool group, and I'm going to put the proportion from preschool. And so what that would be is the proportion of students who went to preschool, or let's, this is a parameter, not who went, so the proportion of students like those in the study who would, and then what would they do? They would, 38 children, and then it was needed social service, who would need social services if they attended preschool. And what's the other parameter of interest? I'm going to call that P sub, let's just C for control group. So P sub C, and that would be the same thing, but for people who did not get to go to preschool. So I'm just going to copy and paste that proportion of students like those in the study who would need social services if they did not attend preschool. And then we know P hat sub P. So P hat sub P, that was the proportion who went to preschool in this group and still needed social services later. So it said 38 children in the preschool group. That was 38 out of 62 who were in the preschool group. We know the sample proportion of those in the control group who needed social services. That was 49 out of 61. So certainly a higher sample proportion than for the preschool group. But will it be significant? We'll find out. And then we need to write our hypotheses in here. So let's get our null, let's get our alternative. And so it works very similarly when we write hypotheses compared to what we learned when it was only one sample. Because still what we're going to do is now we're going to say that they're equal. So P sub P, this would be if there's no difference in the population. Or there might be a difference. So I'm going to write these again, and then I'm going to read the question carefully to see if there's a direction. So they asked, do these data provide convincing evidence that preschool reduces the later need, so that the proportion would be smaller for the preschool group? Okay, so that's going to be a one-tailed test. Now let's write up our plan. Our plan, what kind of test are we going to do? Let's see. Let's go look in the calculator real quick and see what makes sense. So let's go look at the tests that we have at our disposal here. So stats, stat tests, let's see what we got. We are dealing with proportions, and you know what? Very similar to the question we did right before this, where it was a 2 proportion z interval. This is going to be a 2 proportion z test. And so we'll come back and fill that stuff in a minute. Let's continue to answer our question first, because we're getting a little bit of, or I'm getting a little bit ahead of myself right now. So that is going to be a 2 proportion z-test for a difference in proportions. And we have conditions to check. And our conditions are randomness. And do we have that? Let's go see. It says that they randomly assigned the subjects. So I'm going to quote that. We don't actually need to check the 10% condition because this is an experiment with random assignment. You could if you wanted to, but you don't need to. And so the only other thing that we need to check before we continue is we do need to check the large counts condition. And so let's do that. So let's check first for the preschool group. That was a sample size of 62. Our first proportion was 38 out of 62 children. And so our complementary proportion, how many students did not need services, or how many children did not need services, that would be 24 out of 62. Cancel the 62s on both of these, and in both cases they're clearly greater than 10. So we're good there, and this was on the preschool groups. Let's do it on the control groups. So we had a sample size of 61 multiplied by our first sample proportion, 49 over 61. Notice there's only 12 who did not need social services later in life. So that's our complementary proportion. Oops, except it's out of 61. Sorry, that was a mistake. So 61. Cancel the 61s, and we see that both 49 and 12 are greater than 10. So we're all good on the large counts conditions. All right, it goes state, plan, do. So we're down to the do part of things now. So I'm right back to this initial screen now. Okay, and so we had the preschool group. Let's put in the numbers for the preschool group, and that was 38 out of 62. So 38 out of 62. And then I remember the control group had only 61 in it, and so in that group 49 out of that group needed social services. And then we said that it would be less for the preschool group. So there's our alternative hypothesis. And there we go. Our p-value is 0.010. Let's return back to our notebook and record that real quick. Okay, so for do, we had our p-value of 0.010. We also need to record our standardized test statistic, which was z in this case because it was proportions, and that was negative 2.320. And let's draw a quick little sketch. And so if 0 is in the middle, negative 2.320 is there, and this was a less than, so it's shading to the left over here. And so there's your p-value right there. That's our state, that's our plan, that's our do, and so it is time for us to interpret. All right, so since our p-value, which was 0.010, now what do we compare it to? What was our value of alpha? What was our significance level? Let's return up to the question. They didn't tell us what it was. And so if they don't tell us, we're going to assume that it's 0.05. And so what I'm going to say down here, since they didn't tell us alpha, I'm just going to say it's less than 0.05. Another way you can do this, you can say since our p-value is very small, okay, we reject the null hypothesis. Okay, and then we say there is convincing evidence that, what is there convincing evidence of? Let's go see what we set up above. Convincing evidence that preschool reduces the later need for social services. So I'm just going to type that in here, that preschool reduces the later need for social services for children like the ones in the study. Like those in the study. Cool. All right, y'all, and that is it. That's the end right there. Let's do one more, and then that'll be it for today. And here's our last question that we're going to do together. How quickly do synthetic fabrics, such as polyester, decay in landfills? Uh-oh. A researcher buried polyester strips in the soil for different lengths of time and then dug up the strips and measured the force required to break them. Breaking strength is easy to measure and is a good indicator of decay. Lower strength means the fabric has decayed more. For one part of the study, the researcher buried 10 strips of polyester fabric in well-drained soil in the summer. The strips were randomly assigned to 2 groups. 5 of them were buried for 2 weeks and the other 5 were buried for 16 weeks. Here are the breaking strengths in pounds. Do the data give convincing evidence that polyester decays more in 16 weeks than in 2 weeks on average? State. Okay, we can either list out the 2 parameters independently, like we did in the previous example, or we can list them out as one thing. So I'm going to call that mu sub 1 for group 1, let's call it that, and mu sub 2, and that's going to be the mean of the group number 2. The mean difference in, was it breaking strength? Is that what it was? Breaking strength. The mean difference in breaking strength for polyester fabric buried for 2 weeks versus buried for 16 weeks. Okay, what else do we need to say in the state? We need to give some hypotheses. So let's give our null hypothesis here. So our null is that perhaps they are the same. So mu sub 1 might be equal to mu sub 2, so possibly there's no difference. Or our alternative hypothesis, and they ask that polyester decays more, so that's telling us it's one directional. And so if the 16-week stuff decays more, that would mean it would have a lower breaking strength And so the mu sub 2 group is going to be less than the mu sub 1 if that's the case. Okay. And then what do we know? Do we know what x1 sub x bar sub 1 versus x bar sub 2 is? We could figure it out. Okay, let's leave it like this just for the minute. And once again, they did not tell us a significance level, so we're going to just pretend that it's 0.05, like 5%. Okay, so that's our state. Let's go down, let's make a plan. What is our plan here, y'all? Let's go look at our tests and see what we have available. We have... Now this is means, not proportions. So remember, means are t, and we have a 2-sample t-test right here, and so that's what we're going to end up using, but we're not there yet. Right now, we actually need to input the data. So let me back out of this for a minute and go back to my table, which I think was on this screen right here. And so I'm going to call this not group 1. Let's go 2 weeks. I'm just going to call it 2, and then I'm going to say 16 for the next one, just so we know what we're referring to. And then let's type in those numbers real quick for each of those. And so let's go back and continue to fill in our next steps. So again, we were going to do a 2-sample t-test. That was the whole reason we came over here. So we're going to do a 2-sample t-test for a difference in means. We need to get our conditions down. First of all, we hope that there is randomness of some kind. Did they randomly assign the fabrics to treatments? I sure hope so. Where does it say? The researcher buried, they are randomly assigned to the 2 groups. Okay, there it is. Good. So randomly assigned. Awesome. Do we need to test the 10% condition? No, because it's a difference of means. And you know, we have a really small sample size. However, this was a randomized assignment to basically an experiment. So no, we don't need to do that. We do need to establish normality of the sampling distribution. And so let's go back up and look. It's a small sample size of 5 for each. So the central limit theorem isn't going to apply. And then do they tell us anything about, no, so they don't know if the distribution is going to be approximately normal or not. So once again, we're going to go look for skewness or outliers in our data. That's the second time we get to do that today. So let's look at the 16 group and let's look at the 2 group. And let me change this back to a dot plot. I'm not seeing anything obvious here, so we're going to accept it and go with it. By the way, in a free response question, you're never going to get into a situation where it stops right here, unless they told you in the question that it might. They're not going to stop you here. So I'm going to say no apparent skewness or outliers in dot plots of the sample data. Cool. We're down to doing the test. So let's go do it. Let's go back to our calculate screen. Menu, go find that test, 2-sample t-test. And let's plug in our information. So we have data. Yeah, we're going to use data. And our first list is the stuff, and it's just in here in this order, so I'm going to go with it. So 16 and 2. And it was suspected that the breaking strength would be lower for the group with 16. So I need my mu sub 1 to be less than. Now when this 1 and the 2 down here in the alternative hypothesis, they're referring to list 1 and list 2. And so let's see what we get. All right, 0.186 for my p-value. All right, right away that stands out. That's a big p-value, definitely too big. So let's record the p-value. I need to also get the standardized test statistic on here. So yeah, so that already is telling me we are probably going to fail to reject. This is an inconclusive experiment for this experimenter. So let's record what we got. We got a t-value of negative 0.989 essentially, and we got a p-value that was 0.186, and let's do a quick sketch. If 0 is there, negative 0.989 would be there. We're shading the tail area, and that's where the p-value lies. and then we need to go interpret that. So what does it all mean? Well, we're about to say. So what it all means is, since the p-value of 0.186 is large, we fail to reject the null hypothesis. And then what did the square? They said, do the data can give convincing evidence? We have some evidence, but not convincing evidence that, and then we're going to restate the question after that. So we do not have convincing evidence that polyester decays more in 16 weeks than in 2 weeks on average. Now, I said we have some evidence. So what am I talking about? What is some evidence? Let's go back to our calculator output for just a second. So look at the difference in sample means. So in one of the groups, the group that was in for 16 weeks, because I chose that as group 1 when I put it in the calculator, the breaking strength was less. So the fabric that's been in the ground for all that time is not as, for 16 weeks, is not as strong as the fabric that's only been in the ground for 2 weeks in our sample. But the issue is that difference, and for this sample size, it's not a big enough difference to where we can logically conclude that the same thing would be true for all bits of polyester or for polyester in general. Okay, and so that's why this is sort of an inconclusive test where we're failing to reject. So people, that's going to be all for today's video. I hope that was helpful and you enjoyed it, and I'll see you next time.